For more information on Rebecca and its associated Eureka beacons, have a look on the wiki page searching for Rebecca and Eureka. Similar on YouTube, there's a few videos about them both. And lastly, have a look at www.vintageavionics.nl. This is a Rebecca transmitter. It's built into a fairly beefy aluminium chassis. It allows it to be pressurized. It's got rubber seals around everything. This is a transmit antenna socket, and this is the electronics. It's got about 3 sections of it really. We have a motor control unit here, which drives a tuned anode short. This will tune up and down here, depending on what frequency of operation it wants to use. It will typically transmit in the region of 200 to 230 megs. The shorter this is, or the closer it is to the top, the higher in frequency. The more it goes down into the bottom here, the lower in frequency. This lot has its own control circuit. It takes an external voltage from a potentiometer, and it compares it with a voltage on its own potentiometer in here. This is tied in to the position of the dead short. It's got a voltage comparator built into some semiconductor block here, which drives 2 relays, both of them behind here, which are very difficult to see. One drives it in one direction, the other drives it in another direction. And when the 2 voltages compare with each other, are the same, this will stop. And I'll show you a bit of that, just quickly tuning it. There are a circuit on the vintageavionics.nl site, as I've mentioned before. The whole thing has 3 supplies to it. A 28 volts nominal, which is the aircraft voltage coming in, which drives this board. It needs 12.6 volts for the heaters for the 2 valves, and a 300 volt HT, which is not actually for the valves, but it's to charge up a capacitor at the back here. That is, I believe, a 0.5 microfarad cap at 500 volts working. What actually happens is on this little board with the 2 semiconductors, transistor there, this is a blocking or relaxation type oscillator. The first transistor is the oscillator, and it's built on coils, 3 coils on this little ferrite ring. 1 is in the collector of that transistor, 1 is in the base of the transistor, and a 3rd coil is a driver for this output transistor, which is an emitter follower to drive the gate of the thyristor. And that pulses at around about 140 times a second. If that capacitor has been charged up by a resistor to, say, 300 volts, the pulse will come along, short out the thyristor, which then dumps any charge within that capacitor across a pulse transformer, which is in here. That takes the 300 volts up to round about 3 kV. So that's 3000 volts pulsing across the output of the valves. It's only a short pulse, around about 3 or 4 microseconds, but it's enough for these to start oscillating and transmitting out on the frequency they've been tuned to. So this puts out a pulse at about 1 kilowatt level, or just under 1 kilowatt. But because it's only a pulse of a very short duration, about 3 or 4 microseconds, and it's doing it 140 times a second, the average power output is something very low, typically half 0.7 of watt type thing. What I'm hoping to do is show you some pulse train from this thing in a scope that is safely doing it with just 28 volts on that, no HT, no heaters running, so I've got absolutely no chance of putting any high voltage spikes on it because I don't want to damage myself or the equipment I'm going to connect to it. So I'll bring up a circuit diagram of that, show you a little pulse train, not going into too much detail, and let you see how the circuit works. The cap has a charging circuit, which is basically from the 300 volts coming in, it goes through a 2.5 Henry choke in here, and then I got a 3.3k wire wound to the top of that cap. So that charges that cap up to about 300 volts, and quick enough to do it in between the pulses of this thing. On the other side, there's a pulse transformer at that side of this block here, and I say that takes that 300 volts, transforms it to the 3000 volts needed for the valves. That's only estimate figures. I can't put my scope on that. My scope can't take 3 kilovolts going into it. The circuit for the motor drive is on the vintageavionics.nl site, as I think I said. And at the end of it all, hopefully, I should be able to put it into a dummy load, put all the correct voltages onto it, and diode sniff the output on it just to show you the period of RF pulses coming out of it. As I say, I'm going to do that into a dummy load. It's never going to go onto the air. That sort of band of frequencies nowadays is used generally by DAB, and I certainly don't want to cause any troubles to anybody's reception. Okay, moving on to the next bit. Okay, top left we have the 28 volts coming in via a 380 ohm wire wound resistor. We've got 3 coils, L1, L2, L3. These are all on the same ferrite ring. 2 transistors, both NPNs. Bottom right is an output there that's going to fire the thyristor gate. And the timing of the whole device, the pulse generator, is decided by the values of R2, RV1 and C1. That gets charged up when the transistor gets switched on and then discharges through R2 and RV1. That's the 68 and 33k resistor. Little numbers around it, 1, 2, 3 and 4. 1's the gate output, 2 is the collector of the transistor, 3 is an emitter, 4 is the base of it, are all points I'm going to show on the scope. Okay, this is the test setup. It's connected to a small 28 volt power supply. This is the layout. This is the pot I was mentioning before that would change the tuning if I just move it. So going one way, going the opposite way, it will go past a point and then come down again. So, and back down. So tuning of the frequency for this device was done from an external control box. Okay, that's enough for that. Just move back out again. What I've got here is a scope. And if I connect the scope to, first of all, the chassis as a ground, and I shall connect to one point I've found quite useful is the emitter of the transistor, which is there, and ask the scope to sort itself out. You turn off channel 2, and you see a nice little triangular waveform on the emitter, and because that's constant all the time, I'm going to use that as a reference to then show where the other points are. And as this scope will actually store pictures and I can put them onto the PC, I will basically show you the pictures from other points as well, such as the output pulse is there, and switch on number 2, press the auto button, and you'll see there's pulses as well happening on the bottom. So let me go to some stills from the scope. Okay, here's a picture of the emitter at the top and the output pulses to the thyristor on the bottom. What I'm going to do is use a scope to stretch these out so that you're actually looking at the pulses itself. And there we go. This is the charge ramp on the emitter at the top, and this is the output pulse on the thyristor at the bottom, and you'll probably note there it's around about 5 microseconds wide. Next is emitter and collector, and you'll notice the collector drops as it's turned on. That charges up the capacitor on the emitter. The time base is now 1 microsecond per division, so that's a 5 microsecond pulse. And lastly here, emitter and base. You'll notice how the base voltage rises as the emitter voltage rises back up, and the ringing at the end of the pulse as it all gets switched off. Okay, final part of the circuit. The 300 volts now comes in via this 2.5 Henry choke through a 3.3k resistor and charges up the capacitor C5. C5 has got a path to deck on the other side of it. Once that gate pulse comes in from the bottom left there and fires the thyristor, that thyristor, which was previously open circuit, now goes dead short and dumps all that current from that capacitor through that pulse transformer. So that 300 volts on one side generates round about a 3000 volt pulse on the opposite side to power the anode of the two valves, which then oscillate for that very brief period of time to send out an RF pulse. The next thing to do is to try and set it all up properly, put it into a dummy load, and show you these RF pulses. Just a bit of video here just to show the heaters lit up on the two valves. It's proved a little bit more difficult than I expected to actually show the RF pulses, but nevertheless I think I'm being able to show something now. We have 3 power supplies and a 12 volts to 300 volts converter. So that provides the 28 volts. This one provides the heater voltages, and that one provides 12 volts for that block. The transmitter is connected via a piece of coax into this, which is a dummy load, which has a built-in diode probe. Not the fastest, but it's still there and it actually shows some indication. And then this lot goes into the Hewlett-Packard scope, because this is a bit faster when it comes to displaying signals. This is good for like 100 megs type thing. So I might have to turn the lights off so you can see things and move the camera so you can actually see into the scope. 2 seconds. What I'm looking at now, these spikes on the Hewlett-Packard scope, is RF detected pulses. They are every 7 milliseconds, which corresponds to 140 pulses per second. So just taking it out there. So that's 1, 2, 3, 4, 5, 6, 7. 7 to about 7.2 milliseconds every pulse. It doesn't really show you a great deal apart from the fact it's putting RF out. Right? There's no easy way I can show you a very fast pulse. What I can show you though, if I put the light back on, there is a cathode resistor between the cathode of the two valves and ground, and that is 47 ohms. Now, that 47 ohms, as it passes a current due to the high voltage pulse, generates a voltage across it. And that voltage there, let me see, we're on 25 volts per division. It's 25, 50, 75 volts, just over 75 volts across that pulse. It says it's doing actually a pulse of about 79 volts with the minimum. We'll call it 75 volts across that 47 ohm resistor. So that is equating to those valves passing a current of over 1.5 amps every time it pulses. So that's just showing it's actually passing quite a bit of current. That's the whole idea of a pulse transformer, and the pulse output is its high current, high voltage, high wattage, but for a minuscule part of a second. We're talking here of a 5 microseconds per division pulse width. Take it out to 2. So let me think. Probably 3 dB down, or at least half voltage, is going to be round about there, which is 3 microseconds width. I think that's how they measure the pulse width anyway, down to about half a point, half the power level. So there we go. Interesting? Well, I like it. It's interesting. It's taught me a little bit more about things used for navigation and radar type things in the past. And I just hope you liked watching the video. So thank you very much indeed. And I'll try not to make it too long before the next one. Thank you.